What's up, mathematicians? Welcome to section 6.3, nth roots and rational exponents. It's your boy, Mr. Bergman here. Let's get into it. I just want to point out, check this out right here. If you, the short version of what I want to say is 9 to the 1 half times 9 to the 1 half is equal to 9 to the first power. Because, you know, when you're multiplying bases, you can add the exponents. 1 half plus 1 half is 1. And you also kind of know that in a completely out of left field, square root of 9 times square root of 9 is square root of 81, which simplifies down to 9. Look, these are the structure of these is very similar. So much so that, in fact, we can say that 9 to the 1 half is going to be the same thing as square root of 9. So what does it mean to have a fraction as an exponent? It means a radical. Fractional exponents are going to turn into square roots. So you can see 7 to the 1 half. What does that really mean? That's the same. It's going to be the same thing as square root of 7. The 3 to the 1 half power. This is new. We've never seen this before. We're converting between radicals and exponents, and so this exponent here, a fractional exponent, is going to be square root of 3. D to the 1/3 power. Well, the 3 and the denominator of this fraction is going to indicate that this is the cube root of d. We can also go in the reverse direction. So if you're given the square root of 6, you can convert that into an exponent. That's going to be 6 to the 1 half. I'm getting 1 half because of the radical. The kind of square root is it's a square. The kind of root is it's a square root. So it's a 2 right here. There would be a 2 if you had to write a number. The fifth root of 11. So what is the kind of radical here? It's a fifth radical. So we can change that to 11 to the 1/5 power. The cube root of w is going to be w to the 1/3. So that's all well and good, but what happened? So the denominators are going to be they indicate the type of root. The numerator is going to be just a regular exponent. So you could rewrite this as 7 to the 1 half to the 3rd. Like the 3 is going to be a regular exponent and the 2 is going to be in the square root. This is the square root of 7 to the 3rd. You could also write this actually as the 3 could be on the outside as well. Kind of like you see right here. 3 to the 5 halves, the denominator turns into a radical, and the 5, the numerator, can be written on the outside. It could be also be written on the inside like you see here, but I just wanted to show two different versions of kind of the same idea. Numerically, they're going to turn out to be the same. Like, it doesn't matter if you put the 5 on the outside or the 5 on the inside. If you wanted to find a decimal answer for both, they'd be the same decimal. A to the 4/3. Well, you can put the 4 on the inside or the outside. I'm going to put it on the inside. So you can see that the denominator turns into the radical here. What kind of root is it? It's a third root. It's a cubic root. 6 to the 3 halves. 3 is, I'll put it on the outside just because I feel like it. It could also put it on the inside if you wanted to. 6 to the 3 halves, and the denominator indicates what kind of radical it is. It's there it is. Then if you started with the square root of 6 to the 3, you can see this 3 would be the numerator, and the 2 of the square root would be the denominator. Numerator 2, denominator 5. Boom. Numerator 4, denominator 7. Boom. So the big idea, generally it looks like this. You have b to the fraction over x over y. That turns into the x. And what kind of radical? A y radical. And the x can go on the inside or it can go on the outside. There's some conditions on this. You got to make sure that x and y are integers. Like you can't have a fraction in the exponent that also has a decimal. That's going to blow our mind a bit too much right now. Don't want to go there. So x and y are going to be integers. And then y has got to be greater than or equal to 1. And b has got to be positive. This number on the inside is positive when y is even. We're going to challenge that in a second. See what happens when b is negative. So but first let's simplify. Check this out. So x to the 4th, the square root of x to the 4th, that's going to be 4 over 2, which is 2. You can see that the numerator comes from the exponent here, and the denominator comes from the kind of square root. And then you simplify the fraction. It's just going to be the same thing as x squared. X to the 3rd, with the cube root of x to the 3rd, that's 3 over 3. The numerator comes from here, and the denominator comes from here, and you simplify it, you get x to the 1st power, which is just x. Cube root of x to the 6, well, that's just going to be x to the 6th numerator and denominator. It's the same thing as x squared. How about this? The fourth root of x raised to the 16th. Well, 16 is going to be the numerator, 4 is going to be the denominator, and 16 over 4 is 4. So there it is. Now, let's see what happens when b is negative. When b is negative, so like the number on the inside is negative. So negative 5, when you square it, first you get positive 25. And oh look, I can take the square root of a positive number 25. The answer is 5. So we're starting with b is the number on here is negative 5, and it ends up to be positive 5. Negative 3 squared is 9. Take the square root of that, you get 3. Starting with a negative, ending with a positive. Interesting. Starting with a negative, ending with a positive. Negative 2 times itself 6 times is 64. Notice there's an even number of negatives here, so they all cancel out. You get a positive number, and then the square root of 64 is 8. This does. Everything seems. The really interesting thing that I want to note here is that when b is negative, it can end up being positive afterwards. I think we need to examine this a bit more. All of the numbers here on this gray row are going to be 2. X is going to be 2. X is going to be equal to 1 on this row, negative 1, all the way across the entire sheet of paper. So let's examine some things. Let's take a look at what exactly square root of x squared is. You can see when x is positive, like in these first two rows, you get a positive number out. No big deal. That's kind of expected. But when you take the square root of x squared and x is a negative number, negative 1 squared turns into positive 1, and take the square root of positive 1, you get 1. Negative 2 squared, you get 4. Take the square root of 4, you get positive 2. So you're starting with a negative number, ending with a positive number. That kind of smells like an absolute value. So really, you can't say that the square root of x squared is equal to x. You can't, because here, anytime you have a negative number, it just it turns into a positive number. Really, that sounds like absolute value. So what you can do is you can say that the square root of x squared is equal to the absolute value of x. I wonder if this happens for other powers. So again, let's let this x be 2 here. 2 to the 6th power is going to be 64, like we said before, and then take the square root of that, you get 8. And everything's fine when you get positive numbers, but when you have a negative number here, you get negative 1 to the 6th power is positive 1, and then take the square root of that, you get 1. That kind of feels like, and then negative 2 raised to the 6th power is 64, positive 64, and you take the square root of that, you get 8. So you can't really say that the square root of x squared is x cubed like you would want it to. It's really the absolute value of x cubed. Remember, I'm getting this 3 in the cubed because 6 x to the 3rd power divided by, the numerator is 6, the denominator is 2, so 6 over 2 is 3. That's how I'm getting the 3. You can't really, if you wanted to simplify this, basically you can't simplify it down to x cubed. You have to simplify it down to x cubed with the absolute value. Let's take a look over here. So if you're going to take a positive number like 2 and raise it to the 6th power and take its 3rd root, that'd be 4. So 2 to the 6th is 64. The cube root of 64 is 4. Start with 1, end with 1. Start with negative 1, end with 1. Start with negative 2, end with 8. So you could actually say, you could use the absolute values here, but it's actually redundant. You don't need to, because the answer is just going to be x squared anyway. If you want to simplify x to the 6th, the cube root of x to the 6th, here, the numerator is 6, the denominator is 3, 6 over 3 is 2. You don't really need absolute values over here because it's just redundant. You might as well have just x squared. So, what do we know? Here's the big idea. When you find an even root of an even power and the result is an odd power, then use absolute values. So even, even, odd. Everyone say it with me. Even, even, odd. Check this out. Even, even, odd. Even, even. No, this is not even, even, odd. This here, even, even, odd power. Let me show you some examples. The big idea, when you find an even root of an even power, the result is an odd power, use absolute value. So let's practice this. So maybe the even odd power even odd rule is going to be easier to see when you turn it into a fraction, a fractional exponent. So the numerator is 2, the denominator is 2. Even, odd, 2, 2, 1. 2 over 2 is 1, and so because it goes even, odd, we need absolute values. Here, 4, 4, 1. 4 divided by 4 is 1. Even, odd, need absolute values. Here, even, that's not does not follow the rule, so we don't need the absolute values either here. If you were to put absolute values on this answer, it would be a little bit redundant because this is always going to be even. It's always going to be positive anyway, any number you put in for x. So this simplifies down to this, and no absolute value is necessary. Okay, 18 over 2. The 2 comes from the fact that it's a square root. So even, odd. 18 divided by 2 is 9. Yes, you do need absolute values here, because if you were to put in a negative number here, you'd raise it to an even power, and that negative would disappear, and you take its square root. So this is not the same as x to the 9th. This here simplifies down to x to the 9th inside an absolute value. Let's see. Even, so you don't need absolute values. Any negative numbers you would put into here would just stay positive anyway for x to the 6th. So no absolute values necessary. That would be redundant. Whew, that was a lot. All right. Now, anytime you're simplifying radicals like this, you do need absolute values, except here's how Alex is going to say you don't have to worry about the thing I just taught you. And anytime you see assume the variable represents a positive real number, that means you don't have to worry about absolute values anywhere. But if you don't see these instructions, then you have to consider it. So far, we've been dealing with mostly squares and cubes, and so I've been saying things like, all right, everybody, what is 5 times itself? It's 25. What is 8 times itself? Is 64. Or what number times itself 3 times is 125? Well, that's 5. What number times itself 3 times is 27? It's 3. And we've been basically kind of thinking about it in our heads mostly, or doing it on paper quickly. But I just wanted to throw it out there that because Alex starts using higher powers than 2 and 3, it's worthwhile to think about 2 times itself 4 times is 16, 3 times itself 4 times is 81, 5 times itself 4 times is 625. These numbers, Alex.com generally doesn't look at numbers that are higher than 1,000. So I just wanted to throw out that if you see these numbers, this is what their roots are. Like, what number times itself 5 times is 243? It's 3. What number times itself 5 times is 1024? It's 4. So this is mostly just an easy, handy reference right there. Let's see. Just wanted to throw it out there that my favorite Philly ice cream is Bread and Beck's on Germantown Avenue. Got a lot of fun memories taking my kids there, and I don't know if it's the best ice cream, but it's my favorite because just of the fun memories I got there. Have you been to Bread and Beck's? Do you have a better ice cream? Let me know. Tell me about it in class. So next, to split up these difficult problems, we have to remember a couple things. If you have 2 things multiplied inside a square root, you can split them up, and it's the square root of each of these individually multiplied by each other. If you've got a fraction, a square root of a fraction, or a cube root of a fraction, or a fourth root of a fraction, you can say that it's equal to the square root of the numerator and the square root of the denominator. So here's what this looks like. We're going to take the square root of 25x to the 4th. Let me zoom in a little bit. What you can do is thinking about what is the square root of 25x to the 4th is pretty complicated unless the way you want to do this is you want to split up this difficult problem. Why don't you examine the square root of 25 and the square root of x to the 4th individually? And when you do that, you can see, the square root of 25 is positive 5, and the square root of x to the 4th is x to the 4 over 2. So the 4 comes from the numerator. This 4 in the exponent makes the numerator, and the 2 that you can't see here makes the denominator. Simplifying 4 over 2, you get 2, and the answer is 5x squared. All right, let's do this here. We got a number, we got a variable, and we got a second variable. It's a lot easier to consider these individually, so split them up. This is going to be the cube root of 343. This is going to be the cube root of a to the 18th. This is going to be the cube root of b to the 6th. Thinking about them individually, what number times itself 3 times is 343? Well, I got that chart that I just showed you, and that's going to be 7. And then here, if you're going to simplify radicals here, it's a lot easier to do as fractions. So this is going to be 18 in the numerator, and the type of radical is 3. That's going to go in the denominator. 18 over 3 gives you 6. 6 over 3 gives you 2. And neither of these fractions follows the even, odd pattern, so we don't need any absolute values. Here, we've got two different things that are being multiplied, two different factors. We've got the number and we've got this variable expression right here. So I'm going to split them up. This is going to be the 8th root of 256. What number times itself 8 times is 256? Good night. Well, I'm going to guess 2. 2 times 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 2 does give you 256. So that's why this 2 is right here. And because it's a variable expression, I'm just going to use the fractional version, fractional exponent. The numerator is 24 here, and the denominator is 8, and then 24 divided by 8 is 3. And check it out, it follows the even, odd pattern, so we need absolute values. 2 times the absolute value of y squared minus 2. If you ever get a negative number inside these parentheses, you got to make sure it turns into a positive one, because it would up here. Let's go into fraction land. We've got a cube root of a fraction. That's going to be the cube root of the numerator over the cube root of the denominator. And splitting them up, it makes it a lot easier to think about. The cube root of 125, what number times itself 3 times is 125? That's 5. What number times itself 3 times is 343? That's 7. And the answer is 5/7. Here, again, we've got a fraction. The 4th root of a fraction is just going to be the 4th root of the numerator over the 4th root of the denominator. And so you can figure out what number times itself 4 times is 1. It's underneath this red dot. And then you can figure out 625. What number times itself 4 times is 625? That's going to be 5. 5 times 5 times 5 times 5. And are we done? Is that it? All right. Great job sticking with me this way. Can't wait to see you in class. And that's it.